Hi all, we're at Mechanical Equilibrium Part 1. What does a vector have to do with it? To really talk about mechanical equilibrium, we have to touch upon something called a vector. Now, what is a vector quantity? Basically, a nice fancy word for amount is magnitude. So what a vector does is it tells you an amount, or in other words, a magnitude, plus a direction. This is not to be confused with another type of quantity called a scalar. If I have a can of soda, we might say it's 12 ounces. That is certainly an amount. But it wouldn't make sense to say what direction is the 12 ounces. So that would not be a vector. But a vector does have direction. Here's some examples. Velocity. That's how fast you're going and what direction. Acceleration. You can certainly say which way you're accelerating. Think about being in a car. Right, left, back, forward, north, south. And of course, force. You can push on something. If it makes sense to ask, what direction are you blank? It's a vector quantity. The way we show vectors are arrows. With an arrow, we can change the length, and that would, of course, then show how big it is, meaning we have a greater magnitude or a greater amount of something. And of course, an arrow points to some direction. So we have two different magnitudes shown. One's large, one is small, but they're both to the right. We must talk about direction. Some examples. How might you add these vectors? Well, on the left, 7 newtons to the right and 4 newtons to the right. You're going to simply add them together. They're going in the same direction, so here's 4, here's 7. We have a net, or a total of 7 plus 4 is 11 newtons to the right. And we would do the same with the other ones. So these are 4 and 7 up, so 11 up. But what if they're opposite? Well, we would have our 7 newtons this way, our 4 newtons the tail would go that way, and what's left? 3 newtons. You can think of it as walking. If I go 7 newtons to the right and then 4 newtons to the left, what's the total displacement? 3 newtons. So let's do a real quick test. Let's see if you can figure this out. We have a 13 newton and 25 newton force. They're acting parallel to each other. What are the possible resultants? You can, of course, pause the video and think about this. Well, the idea here is the possible resultants. They're parallel. They could be like this. They could be like that. They could be this way. They could be that way. Many different ways. So you can add them. 25 and 13 would be 38. Or 25 minus 13 would be 12. And of course, we would have to say left, right, or so forth. Since there's possible resultants, we could have an infinite number here. What about 13 newton was pushing up and a 25 newton force pushing down? The result or resultant would, of course, be the 12 newtons down. Again, if I go 25 down and I backtrack and go 13 up, what's my displacement here? It'd be 12. We got Curly from the Three Stooges. He's on a scaffold. There are some scales here. One reads 400, the other reads 600. For a total of how much up? 1,000 newtons up. And of course, he's not falling. He's just sitting there, so we can assume that what is up, what's up, must equal what's down. So down must equal 1,000. Well, 400 plus 100 plus what equals 1,000? 500. Lastly, we have to ask ourselves, well, what if they're not parallel? What if we have something really bizarre? Well, very simply, we would use something called the parallelogram rule. If you remember before, we were taking, when we had two vectors in the same direction, we took the tail of one and placed it on the head of the other. So it's no different here. We would take maybe the tail of this one and place it right here, and that's what we did. Here's our original 4 newtons. And of course, we picked this one up. We didn't change the direction. Put it to the tail, and there's another 4 newtons. And it turns out this black arrow right here is the resultant. That is what the answer becomes. There's one major application of this, however. Realizing that in each case here, A, B, and C, and including with curly, they're not moving. Meaning, what's up, the total force pulling up, must equal the total force pulling down. In other words, these two spring scales must be pulling with the same amount of force down, which is her weight. They're equal. The weight down must equal the tension up, because they're not moving. So what happens if we increase that angle? Remember, we can take this and we can put it here, right? We can pick these things up all we want, but what happens? We take this and we're going to stretch it out, which is what we did over here. Well, it turns out that the tension, again, has to equal the weight. In order to get that to happen, this and this are the same, in order to get that to happen is you change this angle. This vector must get bigger. In other words, the tension might be twice as much, 3 times as much, and we'll do a demonstration in class about what happens if we hang something from a straight rope. Try it yourself. Have your brother or sister hold on to one side, and you hold on to the other, and hang something from the rope. And see what happens. See how much force is required to get that rope to go straight. You'll be surprised. What a great question to ask you in class on tomorrow's quiz. So of course it increases, might be double, might be triple. It all depends on the angle. So can you do this? Well, the parallelogram method, again, we have to pick up. It doesn't matter which one. I'm going to choose the bottom, and I'm going to place it, right? The tail of this one has to go on the head of the other. And here is the resultant in this case. I'll do it. So the sum of those two vectors equals whatever this resultant is. Alrighty, let's do a real quick review. Ask if you can do such things. Can you explain how to add vectors when they're parallel to one another? Can you apply the parallelogram method? I probably spelled that wrong. There's no spell check with handwriting, unfortunately. Do you understand what happens if we have something holding up, maybe a couple ropes holding up something, how that's equal to the weight downward? And do you understand what happens to the force as you change the angle on those ropes? Okay, other than that, we are done. We'll see you in class.